So, how you guys doing today? Doing good? Okay, I feel like it's getting really cold this week. I don't know why, but let's start the chapter again. So, quick review from the last lecture. I know you were here last time. We were watching the video on the YouTube. We talked about some ion, the one with the some double bond, two double bonds, not just one. They can interact with something that we call, so this is diene. So you have two double bonds, so it'll be diene. And this is the one that's going to interact with the diene. We're going to call this dienophile. You get the longer chalk. So these two will make some type of, this type of interaction here. We discussed briefly pericyclic reactions, which we'll cover in chapter 30 in more detail, but this is what they do. So they can make finally this compound. So these type of reaction we call last time Diels or the reaction. Okay. So there's all the reactions. This is what one type of the pericyclic reactions in organic chemistry. But if you guys remember this also from the last time, this might be a very poor dienophile because the if you have a really good dienophile for use can be used for diazo directions, they always have electron withdrawing groups. Meaning they need to be somewhat electron poor, where you can do some interactions with these two. So this won't be a very good. It will be poor dienophile. But if you have anything that has like this one, like a propanol, or some like the aldehyde or the carbonyl groups that takes a little bit of electron to themselves, so that makes this a bit more better nucleophile, kind of behave like a nucleophile, that makes the better dienophile. Okay, so it'll be easy. This will be easier than this one to make. There's our direction with diene over here to make cyclic compounds as a product. Okay. So this is what we did. There's another thing at the end we did was if that comes into certain directions. So we have let's try to make a better one. Okay. So once again, you can have this one instead. Okay. We have this type of pantenoid which is the groups over here. Oh, sorry, even better pantenoid groups over here. And then if that is the case, you have also, relatively speaking, better dienophile than before because of this group, electron within groups. So they're going to have a certain diazo direction for sure. Over here, over here. So what it really does, once again, is just try to move a pair of electron in the p orbital in this way. Okay. So this is how they make cyclic compound part of your products. So outcome will be this one. Looks like this. So you see the location of double moiety here, and then those two make single bond to the previously alkene part. And then you can try to draw in this way. This one, okay? So if you look at this one, look at this dienophile, obviously it has all groups, the much prior groups on the same side. It more gives the Z conformation, you can also say the cis. It also gives the product that also shows the same addition over here. So you see those two R groups are heading backward, right? With this dashed line over here. And there's two hydrogen also were in the same side, also heading front. So it also gives very good cis products. We're gonna call this type of reaction stereo specific, because the chemistry-wise, it's very specific from the reactants to the product. Once it has to the alkyls bond to the same side on the double bond over here, and also the hydrogen to the hydrogen as well, they should be on the same side as in the product form as well. So this is what we did at the end of the last lecture. So that means if you switch this one to more like a trans or E configuration, the only thing you have to do, just make sure they are now on the opposite side, right? So you can put those two on the opposite side. That makes trans products. It is indeed the stereo-specific reactions. You can take a look. Okay. So this was the last part we did on Monday. So let's move on. Can I move on, right? Okay. Let's move on. Okay. So if that is the case, we know that is stereo-specific. The where that it has in the structure reflect the form of the product. We also have a very good dienophile. I'm sorry, not dienophile, diene. Looks like this one. So this is the 1,3-cyclopentadiene. Cyclopentadiene. So it's in the cyclic compound. We also have a really good dienophile too. That is the maleic anhydride. So if you look at this one, this is really good dienophile for sure, right? So if you look at the groups on here and here, which makes very electron density poor region of where you can have a double bond, and this the dienophile. So that makes even better dienophile. That makes even better deals all direction, easier and faster. So if that is the case, the thing is that this diene, the cyclopentadiene, has a ring structure. So what happens to this one is still same. Whenever you have the p orbitals on 4, and they're going to bond to over here in this. Okay. So they makes kind of a weird structure. If you look at this one very carefully, what it happens is they two make. Okay. So this is this carbon. It's right here, and these are over here. You see the 1, 2, 3, 4, 1, 2, 3, 4, and there's a new bond we made to this one, and double bond will be gone to making these two. Okay. And then whenever you have this ring structure here, the cyclic part also heading down, and you don't see it here. Let's read it real quick. So you don't see it here very well, but you also have what? Hydrogen, because you always think that it's an implied hydrogen there too. So they're going to show you in this one. Okay. So if you just try to do the single bonding, that is what it looks like. Okay. So this is indeed kind of a weird bicyclic compound, right? It has the one breach and two. There's another one that connect to your other dienophile. So if you have this type of thing, there's another possible scenario is the this one. You have so if you have this one over here, it's the same here. In case you're going to put those hydrogen on the downside, and this one. So there is two possible products If you see this, the stereochemically speaking, right? But this is what we call Indo products. Oops, sorry, Indo products. This is what we call exo product. So the between these two, interestingly, I hope you guys remember this one. Only Indo product will be found in this bicyclic compound over here. So the Indo simply means it's a same addition to the direction of your bigger bridge on the bicyclic compound. So let me get that first. So if you look at this weird structure, you have a bridge on these three bridges: 1, 2, 3, 1, 2, 3, 4, 1, 2, 3. So it has a bridge of 1 carbon here. Okay. These two have a bridge of 2 carbons here. So this is a carbon 2 bridge, carbon 1 bridge over here. If you're the dienophile attached to the same direction where you see the bigger bridge carbon, that is what we call Indo. So if you look at this one over here, those bigger bridges in carbon 2, this is only 1, so this is a bit bigger and shorter one. That heading downward. All along here it's down, and also heading down and down. So if your dienophile addition to your bicyclic compound that shares the same direction down, down, is what we call Indo. It's a symmetry. If you actually go in opposite direction, it's going down, up, down, right? And we call this the anti-addition, right? And that is what we call exo products over here. But interestingly again, we don't find this in the there's 2 combination here, only in the product here. To explain why, it would be really great if you can watch the last lecture, but it is because of the bigger area. There's the p orbital can overlap to in this dienophile in the endo product positions. So if you want to do it in this way, will be they only experience the smaller area. They can make the bonding, single bonding. So they can be very unlikely happening in here, but this is much easier for them to conjugate because of the p orbital shape in the top and bottom, top and bottom, top and bottom, top and bottom. So you don't have to know for this one. You only need to know for it's always going to be Indo in this type of bicyclic compound situation here. But I'll just explain why, but you don't have to know this for the exam. So what happens is this one. So whenever it has to comes to in this way, they're actually going to end either here or here. Right. Okay. So if they're bonded to in this way, you see the hydrogen will push down, right? But if they bonded to in opposite directions, hydrogen will be in the up position. So that was why when they bond to each other in Indo, it gives and they're heading the down way. Do you see it? Kind of. So the only thing that you really need to know is because of the larger area with the better condition between p orbital from here and to here, when this type of bicyclic compound product will have only Indo products. So let's do this in 2D. Okay, I'll make it. So if you do this one 2D, so once again, comes in, okay, comes in. Yeah, I understand. This is really hard to look at in 3D. It's written on 2D. So let's do it on 2D then. Okay. If you really see this one in the exam, right? The product will be looks like this one. Okay. This will be the ring structure, right? Here, so this is the bridge, shoulder bridge. So I'll draw the 3D on the top. So if you do, okay, bridge, right? You have a bond here, into in this way, right? Okay. So that's why you're going to have a wedge. So this is the answer in 2D in the paper, but that's what it actually looks in the reference. Okay. So this is why this is kind of also kind of wedge-like, like a line there. So this is here, 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 here. Okay. But the point is just know there will be endo. So this is why they have this one. All right. Can I move on? So the only thing you really need to know that will be this one because of the endo product is the only thing they're gonna take for the product. All right. So let's do a little more practice. Okay, only here. I know this is kind of a lot of things to think about in 2D and 3D. So let's do practical problem over here. So if you have this type of thing, let me draw in the other way, which is the same, but it'll be easier for you to look at it. So if you have this one over here, if it comes into benzoquinone, okay. Okay, looks like this one. Okay, and then obviously you know for sure this is going to be now in here, here, and here. Okay, so the outcome will be this, right, and the single bond. And then there's also hydrogen over there too, right? So to make it more specific with the hydrogen position, it looks like this. It's the same reason. It would be easier for them to, they can be on the end of position. So if you can just figure this one out, that's pretty much it for the exam. Just diene comes in to the diene file, make a cyclic parts of the products, and that goes into either same. So if you look at this ring structure, obviously there has to be in somewhat what, either cis or G configuration over here, because this ring is kind of forced there. So they all show you cis product like this, because the ring cannot do trans like it's rotate, right? So this is kind of another practical problem you can try. It kind of makes sense, right? It's a stress specific. It's a bicyclic. So anyway, if that is the case, let's try to talk about the exceptions. Okay, let's talk about some exceptions over here. So if you have a diene file over here, this is kind of looks like this, but this can be rotated, right? This can be rotated, right? So in that way, you can also do this one. They can go back and forth. This is a single bond, right? Is it a single bond? They can go on either way. Okay. So we kind of name this one here is this is a single bond rotating, right? So the single bond, and this is in the cis position, right? Okay, and then this is also single bond trans. So we call them S cis conformation and S trans conformation looking go forward. So even though if I give you maybe this one, you can always assume that sorry. You can always assume they can go in this way as well, right? So you can rotate the single bond. It's just the way they put the two double bond at the end in cis or trans position. But the good thing about this one is what? You can actually rotate the single bond, so it doesn't matter. It's okay to get this one to this one, and then they can do reaction, no problem. Because even though it's trans, it can be in cis form anyway by just rotating the single bond. Makes sense, right? So that is the case. But for a certain case, you cannot do this one. There's mainly two scenarios. If you have a bicyclic compound like this one, and you have this. Okay? So in this case, you cannot rotate. You cannot rotate the single bond. It's fixed in the ring structure, right? Makes sense, right? So in that case, it will be fixed only as trans conformation. But the problem is, as we did so many times, it has to be in S cis form to do the Diaz all directions, right? But if they do transform as trans, that would be really hard to make Diaz all directions like this because of the distance and twisting the way they have bonded in the structure. So the S trans one will not do Diaz all directions because of this position. It has to be in cis form to do the Diaz all directions. Okay? So that means this one is also a type of diane, but it cannot do the other direction because it's fixed and transformed. It's fixed and transformed. Okay, makes sense, right? Because to do the other direction, they need to be in S cis form conformation, but now in trans, but it's in the fixed in the ring structure. You cannot rotate, even though it's a single bond. So you cannot do the other directions because you cannot do as cis conformation. Makes sense, right? Okay. So this will not do the other direction. Okay, there's an exception here. And then just one more thing is if they experience very severe static hinderness, if you look at this one, okay. If you look at this one over here, it is experiencing, because of this, the proximate distance between these two the R groups to this double bond on top and bottom. This is its form, but because of this static interference, where it gets a hinderness, they will not do in cis form, so they will do transform instead. So in this case, also they prefer the transform because they don't want to experience the very much of the discomfort they need to experience in cis form. They also do most likely just S trans conformation. So this one also will not do the other direction because it cannot keep the cis form very stable. So two possible scenario. Even though they are diane, if it's fixed in the ring structure where they experience a very strong static hinderness because of the position where it's very close to each other, they still cannot be used for the other directions. kind of makes sense, right? Okay. So there's two exceptions, major exceptions. But other than that, you can free to rotate it. There's no problem. So let's try to do some more practical problem with this exceptional case. If we have this one comes into the lake anhydride, which is very good dienophile. What might be the product for this one? Okay, they can try to. So this is the diene, comes into maleic anhydride, and what might be the product here? Okay. So what might be the product here? There will be no product because they cannot do this. It's fixed in transform. So there will be no products. If I put this on the exam, you need to say there will be no product because of this bicyclic can do this. Okay. All right. So does it make sense? We good? No. Yeah. So let's do this one maybe. How about we do this one? Let's try to change this one to benzoquinol. Okay. And what might be the product over here? So this, in this case, this is in cis form, so we'll do the diagonal directions. So we're gonna draw this one. See the one have electron down here, goes over there. So the final product this one over here. Same here. What's this? Makes sense, right? Because this is in cis form, so it is okay. Even though it's a fixed, but they fix in the cis, so it's okay for them to do the other direction because they're already in the cis form. So you can get the products, no problem. Makes sense, right? Because they're already in cis form. See this? Okay. So the other direction. Let's do one more, okay? Let's do one more. How about we do this one? If you have this one, okay? And this one, I'm gonna put this in this one, and maybe you can try this one. I'll give you about 2 minutes. The first thing you need to see is if it's possible to do that the other direction or not, and if it's yes, you can go ahead and do the other directions and see where they will. Okay, just 1 minute. You can try it. You can try to rotate the single bond, and you can see if you can put it on the cis form, as a cis form, and then try to do the DHR direction on the diene, and then you get the products. Okay, so if you do this one, it is actually can be in cis form because you can rotate this one. It's not fixed in the wing, so it will become this was same as oops, this, right? So no problem. You can rotate it, right? And then you can try to put this one on here. Like this, okay? So now you see they can go this way, okay? So then this will be gone, 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 and here. Okay? So there will be two single bond, which is this one. And once again, make sure you put this. Okay, so that would be your direction products. So it is possible because that had no problem with rotating just a single bond between two double bonds in diane. So it is the directions. Right? Okay. Okay, so the do you want to do one more? Or can I move on? Can I move on or one more? Oh, good. Okay, perfect. So let's move on. So if this is the only thing you have to know, okay? So make sure you have the SSS form of confirmation of the diane, so you can do very good DLR direction with a good diane file. So the next part is the if you have the diane looks like this. You can actually polymerize your dienes with the pair of electron in p orbital, look like this and this. So there'll be like a polymeric chain reactions. You can do with a lot of dienes, looks like this 1,3 beta diene. And then you can have either cis form. Okay. You can either have a cis form, the product where you have a double bond attached to a hull. And this transform too. Okay. So this is the good thing about the how you can use diene also for polymerizing those the molecules so you can have a polymer. What is so good about this one is if you have a do you know how we make the rubber? So if you have this one, and then you're going to have so this is isoprene. They can also do diene polymerization too. Then if that gets to the cis position, we can make rubber from using natural product from tree. And trans is the one that we use for dental treatments. I don't know if you have any dental problem before. This is a bit more brittle product than rubber, so the dentists use them for treating some dental conditions. So this is something we can do with diene for polymerization, making some good rubber. They can also do synthetic rubber synthesized, not from the natural product like tree or other, but this is something we can do with the diene as well. To be honest, I don't think I'll put this in the exam, but this is very good to talk about, at least in organic chemistry too. That's it. So I'll move on. Okay. So the last part of this chapter is about the UV spectroscopy. Whenever you do this one over here, as we know, we have a 4 state with the 4 p orbitals. Okay. So we did this one, and those are the pies. This is the anti-bonding ones. And then if you think about you shoot the light in the UV light on there's the one that electrons in the p orbital, in the pi bond, they can be excited to the LUMO. Okay? So I talked about this one briefly last time, and we tried to explain how we do the reaction. This simply means lowest unoccupied. Sorry, this is the unoccupied molecular orbital. Molecular orbital. This is the highest occupied molecular orbital. So this is why this is the highest one with because this is empty. So from here, the lowest unoccupied molecular orbital is here, and the highest occupied molecular orbital is here. Diagrams over here. So when we shoot the UV and light in here, there will be. This means simply the energy gap. This is amount of energy gap. Meaning, this is amount of the. Oh, sorry. This is amount of the energy they need to have to be excited into LUMO. Okay. So when you shoot a certain amount of energy in UV light, when it close to that specific amount of energy, because there's the energy state is quantized, right? We learned this in Jenkins 1 and 2. There's the energy level is the quantized, meaning it has to be very specific. So if you get to very specific wavelengths, which is lays in the sun range of the UV light among all electromagnetic light spectrum, that gets to they jump to this position over here. Okay? So in that case, meaning when they have a one electron jump to the next level, meaning they're going to observe the light, because it's same as they're observing the energy. So to make this into pi orbital star excitation, so they can put the one electron on the LUMO. Okay, so then they're going to have an absorption spectrum on the graph, because it only happens when it absorbs the energy. Okay, makes sense, right? Does it make sense? Okay. So when it does that, we try to measure the absorption of the UV light using absorbance value, which is A, and the log, and we put the here. Okay. So this is incident light, meaning initial light before it went through the sample, and this is when it after. This is the light after transmitting through the sample. That will give you some number for observance. Okay. So if you have a lower and lower, you have a higher and higher number of observers, which kind of makes sense, because if you have a light, maybe 100 goes in to a sample and only 1 came out, that means it observed a lot of light. That will give us very high number and observance value, because this is the denominator in this fractional number in log. Okay. So the one thing I'll stop here today, but the one thing I want to point out is this observance has no unit because of that. Because this is the intensity of the light, but they cancel the top of the light. So there will be no unit for the observance value here. And we're gonna do it I'll do it later, but the objectivity with the over concentration times the path length. But we'll do this on Friday. So I'll stop here. Let's do the exercise.